What'd you get for 7 pi over 4? Sine of 7 pi over 4.
Negative 1 over root 2.
I think so, right? Because the way I think about this, a few different ways of thinking about it. But you have 1 pi over 4, 2 pi over 4, or you could go 8 pi over 4 is this guy right here. That's the same thing as 8 pi over 4. You bring him back by 1 pi over 4, which will bring you down by 45 degrees. That's 7 pi over 4. And then, if that's the case, what's this angle right here? Pi over 4. Pi over 4, right? And so we know if that's pi over 4, so is the other one, but this is 1 root 2 and 1. And so you could say sine of that guy is 1 over root 2. So, but the thing is, right, and so this is what I've put right here. So we could think about this a couple different ways. Either you take this guy and shrink him down, right, by dividing everybody through here by root 2. Making this height 1 over root 2, making this width 1 over root 2. But since this guy is negative and sine is this one over the hypotenuse, right, then, or we could think about it as just the coordinates, right, that the height here is actually a depth, I guess, right, and it's negative 1 over square root 2, so there we go, this is negative 1 over square root 2. We're going to be doing stuff like this today, although I'm really, well, you'll see. We'll get into it. We'll get into the way I think about doing these guys. It's a little bit different. Okay, so what about cosine 4 pi over 3?
Negative 1/2.
Let's check it. So this guy is 3 pi over 3. One more of them will be 4 pi over root 3. You should know where these guys are, because that's going to make your life easier. And so then, if that's the case, then what's this angle right there?
Pi over 3.
Pi over 3. Now you'll notice, this is the great thing about radians, is that all of those radian measures that I have you memorize, right, like 4 pi over 3, what would this be? 5 pi over 4. The other one here would be 4 pi over 4, then 5 pi over 4. 6 pi over 6, so wait.
7 pi over 6?
7 pi over 6, yeah, right? All of those guys, whatever it's over is the reference angle, right? Like for instance, this is 2 pi over 3. One more of them gets you to 3 pi over 3. So in other words, you take 3 pi over 3 minus off the 2 pi over 3, and you're left with 1 pi over 3, then that means that's pi over 3 right there. Right? It's the same thing with all of them. If it's over 4, then the reference angle is pi over 4. If it's over 3, the reference angle is pi over 3. And finally, if you have, say, 5 pi over 6, you need one more pi over 6 to get you to 6 pi over 6. And so this reference angle right there, which is always, always, always measured from the thing itself to the x-axis, right? That's how we're always measuring the reference angles here. Okay, but anyway, we're going to use that. So the 4 pi over 3, we know that the angle we're dealing with is the pi over 3, which is this guy, pi over 3. Making these sides what?
1, 2, 2,
2 root 3. And we are looking for cosine of that. So cosine of this would be adjacent over 2. So in other words, since cosine pi over 3 is 1 over root 2, 1 over 2, then this thing is just a question of, is it positive or negative?
Positive. Because it's a double negative.
No, but the hypotenuse is always.
Oh, yeah.
Mm-hmm. Careful. And it's better to think of, is the x out, because you know cosine is the x value. If we're talking about being on the unit circle here, right, if that's the unit circle, unit oval, then it reduces to something very simple. Cosine is simply this value right there, right? It's simply where the x value shows up. And if the x value is on this side, it's negative. If it's on this side, it's positive. The y value, which corresponds to sine, is that and that. Now, tangent will be positive over here, because if you took tangent, you would have, you know, whatever. But, so, it would be negative 1/2. There you go. Okay. All right. Is there another way to get a negative 1/2 for cosine? Because look at this, and I drew this terribly, but if this is also pi over 3, right there. Yeah. Yeah, look at that, right? If that's pi, if it's 2 pi over 3, so if I told you to compute cosine 2 pi over 3, you'd go through the same kind of thing, you'd find out where it is. You could shrink a triangle if you like, or you could just go straight to this and say, well, cosine is 1/2. And so it's got to be, this thing would be 1 over, or 1/2 over 1, or whatever, right? But then we just have to ask ourselves, is the x value positive or negative there? And you say, well, it's negative, so it's negative 1/2. Interesting. So, this is where we pick up today with what we're doing. The unit circle is not the best way of thinking about this. So, we will be using the unit circle, like, in order to, just at least at first, this is the way that, you know, I think will be good to get into this. But, you'll see. You'll see. I'll just shut up for a second. Okay, here we go. So for number 42, it says, now here we go, find, this is for all of these problems in this section, find exact values for x in the interval 0 to 4 pi. Okay. And then 42 gives you this. It tells you that sine x is equal to, it says negative root 2 over 2, which, by the way, is negative 1 over root 2. We already found one of them, didn't we? Like, that was the first thing we did. We found that if you plug in whatever, but then, like, kind of like I was saying with the cosine, it's like there's another one out there, right? And when you're just looking at the unit circle, it kind of gets hard to see where the other one should be. And what's more is we're not just talking about from 0 to 2 pi anymore. We're kind of talking about wrapping around the unit circle like 2 full times, once and then twice. So we get now the unit circle is not the best way of thinking about this kind of thing. So we're thinking about what inputs is going to give me negative 1 over root 2 as an output for the function sine. The best way of doing this is to draw a graph. And we're going to graph it on this interval from 0 to 4 pi. So I know that sine starts here, comes up, goes down, comes back up, goes back down, and comes back up. How do I know that? Well, I know that that's 1 full period, so I know that that goes to 2 pi. We're going all the way to 4 pi, so we're doubling everything, so 4 pi. Now, what's going to be really helpful for this is to also, just like we've been doing, we want to get not only every place where it crosses here, but we also want to get the maxima and the minima. Right? I'm not sure if I said this explicitly. Maxima is the plural of maximum. This would be one, you have one maximum value. This is a minimum, that's one minimum value. And so all of the maxima and all of the minima, which occur where? What's the height here?
1.
What's the height here? Negative 1, okay? So we have, this is pi, this would be 1 pi, 2 pi, 3 pi. We have, what's this?
Pi over 2.
Pi over 2. What's this?
3 pi over
3 pi over 2. This would be
5 pi.
5 pi over 2. Finally, 7 pi over 2. Now, okay, so what this is asking here is, where is sine equal to some negative number? Now, I'm not going to try to figure, well, 1 over root 2, that's like 0.707. Doesn't matter, it's negative. And so qualitatively, if I just draw a line right here, and I'm going to do a dotted line, I could see that it's going to intersect the graph of sine at exactly 4 places. And so when the output is negative 1 over root 2, I expect 4 answers for x. This is very similar, and this is what we were going to start off with, is if you had one of these types of problems from like last year, right? And you have some kind of parabola or whatever, and we want to know, like it's the height of a rocket after it's been launched or whatever, and you want to know at what times, plural, is the height equal to say 100? Well, graphically, you could do this kind of thing and say, well, I expect there to be 1 here, and there to be 1 here, right? This could also help you if they ask, at what times will it equal 50? And you could say, ah, look, I'm expecting a negative number and a positive number because it would intersect over here where it's negative. And you could use that information to kind of check your answers and make sure everything's good. Although with this kind of question, you could just plug it in, right? Like you have, this is your function f of x, and then you just set f of x equal to 100 and solve. This is still a little bit different, isn't it? Like, let's solve that. Well, I could, like earlier, I could find you 1, but I'm not exactly sure on this interval exactly how many there should be. So graphing it's really going to help us out. It's going to do something even more. And this is what I really like about this. So I do want to think about the unit circle briefly. So let's think about, okay, when we're here at 0, right, then we're right here. 0 radians, or 0 when x is 0, we're here. Now, as we start to move off, we're in quadrant what? 1. And then what radian measure is this? Now we're in quadrant 2, and then we go, what's it? Pi. Now we're in quadrant 3. And we end up at 3 pi over 2. And then we're in quadrant what? 4. And then we're back at 2 pi. Now, here's the thing. Graphically, check this out. Everything that's here is in quadrant what? 1. This corresponds to quadrant 1. Because remember how this thing was derived, right? We imagined, did you guys get my email?
Yeah.
Did you play with it? Did you see the projection, right? That's all this is. We're just projecting a point on the unit circle as it's just moving around, right? And so when the point is here in quadrant 1, then the thing that gets drawn is here, right? And so if this value occurs here, then what quadrant are we in? 4. Wait a second. What quadrant is this between this value and that value?
It's 3. No, yeah, 3.
Wait, oh,
Yeah, because we're between pi and 3 pi over 2. So, okay, that's quadrant 3. And what about this guy? This occurs where?
That's 4.
That's 4. So I'm going to go ahead and label these. We're going to call this one x1. We're going to call this one x2. Here's another intersection. We're going to call that x3. We're going to call this one x4. So we're looking for, you could think about it as the angle which will give us, let's start with x1. Now, this is how I think about this. First off, I look at this, and I'm not even going to think about any of this right here. I'm just thinking, is there a triangle I know that has one of these numbers in it? Which triangle of the triangles we know has a root 2 in it?
45.
Okay? All right. So that's where I'm starting with all of this. Looking at the output, I can see there's only one triangle I know that could possibly give me root 2 as an output, and that's this bad boy right here. Then this guy is that. And so, kind of working, now I'm going to think, well, I know that x1 is in quadrant 3, right? That's what this means right here, that x1 is in quadrant 3, right? And so, I could say, well, again, coming back to the reference angle, it must be that this bit right here has my pi over 4. Does that make sense?
Yeah.
Yeah.
Yeah, right? Like, And you could, if you were so inclined, take this thing and rotate it and then shrink this down, and you would end up with a 1 right here, a 1 over root 2 right here, and a 1 over root 2 right there. This guy would be negative, which lo and behold is exactly what you want, right? But this isn't, pi over 4 isn't that, obviously. Pi over 4 lives over here. So, again, I suggested that you memorize where all these spokes on the wheel come out. What is that one? What radian measure is that?
5.
5 pi over 4. So if we measured all the way from here over, which is the x value that we want, that's x1, it would have to be 5 pi over 4. And so x1, we're going to start keeping track of these. x1 is 5 pi over 4. Any questions on the reasoning I went through in order to get that first point? Just briefly, again, graphed it to make sure I knew where all my points are going to end up. Took note of what quadrants they're going to end up in, although we don't really need to get to that point just yet. What's really important here is then I looked at the output and said, is there a triangle I know that could, without sine, we're not going to worry about the, without the plus or minus, that could possibly give me a root 2 as an output. Yeah, it's this one. Okay, well then the only way to do this would be that we are going to need, it's either going to be, because the only ones that are pi over 4, I'm sorry, so then I use that to give me what this angle must be. And then knowing, like, well, it could either be this one, this one, this one, or this one, because that's where all the pi's over 4 end up, right? And so then I use this to say, okay, well, if he's in quadrant 3, it has to be over here. The only one with pi over 4 in quadrant 3 is 5 pi over 4. So it must be 5 pi over 4. And conversely, just to kind of check myself, I could just see what would happen if my problem said compute this. Well, I'd find 5 pi over 4. I'd go, it's right there. Okay, up the reference angle is pi over 4. Sine of pi over 4 is 1 over root 2. So it's going to be either plus or minus 1 over root 2. And then I could say, well, since the y value is negative here at this point, because remember how this graph got, like this is what we're talking about really. Everything comes down to where is this point on the unit circle, right? That's how this graph got drawn. As this went around and got to here, this went up and then came back down to that point right there. That's that. And so the sine value is the height. It's negative, so it must be negative. And I could see, yep, okay, yeah, that does give me negative 1 over root 2. And 5 pi over 4 is indeed in this interval that they've given me. It's right there. And so that's x1. Now what about x2? Where is it?
Just loop it. 1. Oh wait, no, never mind. Never mind.
I didn't hear anything you said.
It's in quadrant 4.
It's in quadrant 4, and it's
Between 3 pi.
and it's again the reference angle must be pi over 4. Otherwise, you couldn't have taken an opposite over opposite over hypotenuse in order to get this root 2. Once you figure out like which triangle you're working with, it's very simple. Like that's where all of this comes down to. Once you know which triangle you're working with, you have your reference angle. Once you have your reference angle, well, there's only 4 different possibilities of where this thing could be. And in this case, what would the actual full measure of this one be?
7 pi over 4.
7 pi over 4, which was the one we started with, right? Yeah. So if I measured from here all the way over here, x2, x being an angle we're talking about, right? x2, that angle would be 7 pi over 4. And now I'm just going to kind of double check and look, right? Does that make sense? Does 7 pi over 4 live between 3 pi over 2 and 2 pi? Yeah, it does. Now for these other ones, you just loop it, right? So like if you think about it, we know that from here to here, it's off by 2 pi. And so it must be the case that as I slide everything forward, nothing's changing. This is a periodic function. It comes right back to where it started. And so if the difference from here to here is 2 pi, then if I slid it, we'd also have 2 pi between here. So in other words, what I'm saying is that the x3 that I'm looking for is the same thing as if I took my x1 and then just added 2 pi to it. We know that x1 is simply 5 pi over 4, and adding 2 pi, you could write that as a over 4, 8 pi over 4.
So 13 pi.
13 pi over 4. Does that reduce?
No.
No. Last time I checked, it did not. 13 is prime. So we have x3 is 13 pi over 4. x4, I do the same thing because I just say, well, I know if I add, and please use the graph, think, because and later on, when these get a little bit more difficult, we're going to need to really be thinking about this in terms of symmetry and how much to add to this and how far is this from here to here, how far is this from here to here, and that's going to help us out a lot. Same thing right here. You need to be able to identify this point on this graph, or this point, or this point, or this is always off by 2 pi. So it must be the case that from here to here is another 2 pi radians. And so x4 is x2 plus 2 pi radians. x2 was 7 pi over 4 plus 2 pi. You told me that was 8 pi over 4. So 7 plus 8 is what?
14. No. 15.
I don't know, whatever. I'll believe anything you tell me, really. 15 over 4. Okay. And that's 3 times 5, so that does not reduce. And there you go. That's your answer. Find the exact values for x in that interval. They're all in that interval. And you can see how the graphing is going to really help you keep this straight. And you'll notice I also used a unit circle, right? Like, I would suggest that for each one of these that you do, somewhere on your page, like I would like this to be detailed and look really nice because the more practice you get drawing sine, drawing cosine, drawing all these guys and labeling the interesting points, just the better for you. But the other part with this, like, this is really just to help you. If you just scratch this out and you say, well, I know it's pi over 4. I know it has to be in the third quadrant. And so I have this kind of thing. Okay, and then, like, if that's all you draw, just so that you could know, okay, wait, over 4, pi over 4, that one's 5 pi over 4, right there. That's fine. Like, it doesn't need to be too detailed. This is more to just help you out, you know. Now, for number 51 and 53, it's basically the same setup. They're going to word it a little bit differently, and then there's 2 more interesting things they're going to throw up here. So it's, instead of it being this, they're going to give you this. Then they're going to tell you that A equals this. And then there's going to be 4 parts, or 3 parts here that they want you to do. One, it's going to say, where is y equal to A? That is exactly this problem right here, right? That's the exact same thing. Like that's right, like they're just saying, where is y equal to A? In other words, where is the output of sine equal to the value they gave you? It's the same problem as the ones that you're starting off with. Then they want to know the interval on which, or intervals on which y is less than A, and where is y bigger than A. So let's do that for this one right here. I want to go ahead and knock this out. So y equals A, we got it. There's your answer. That is where the output sine x is equal to A, which is negative 1 over root 2.
And is it the same like 0 to 4 pi or whatever?
Yeah, or it might be different in there. But this is how we're going to do it. It'll give you an interval. It'll give you an interval because otherwise this is infinitely many problems, you know. And that's actually, it's not bad because once you find one, then you just say plus 2 pi for each one of these. You know, like you could say x1 plus 2 pi times n, where n is an integer and it goes on forever and ever. It's not that hard to write down. But they will give you an exact or a definite interval and ask for this type of thing. And so A, we've taken care of. That's the answer to A. B, where is the output of sine x less than that value? And so this is where the graph is going to help you. You could just say, well, we're talking about the height of this. This is where it dips down below that, right? The graph of sine, that's all this means. The graph, the output of sine, dips down below the value A here and here. And so there's two intervals, right? This interval right here from x1 to x2, and then this one from there to there. And if it's strictly less than, so in other words, the answer for B is going to be from here to here. We know that that's from 5 pi over 4. I need some room. 5 pi over 4 up to 7 pi over 4. Should I use hard brackets or soft brackets?
Soft, because it's...
Yeah, now if it were this or equal to, well then, where it's equal, you would include it, and so you would include the endpoints. This one in particular is not. Now we're going to union that with the next interval, which is from here to here, which is from there to there. So from 13 pi over 4 up to 15 pi over 4. And I cannot tell you how important this will be for calculus. Like being able to do this right here, given a function, find out where it's above, find out the interval on which it's below something, or the intervals on which it's above something. This is so important in calculus. It will be, if you get this down now, if this is a really good exercise. This is why I really want you to do it. Okay, now let's do the next one. Where is y bigger than a? Give me the first interval, because I can tell you right now there's 1, 2,
From...
it looks like 2, so yeah.
From, like, 0 to x1.
From 0 to x1, which is, what's x1?
5 pi over 4.
5 pi over 4. Now, soft or hard bracket?
Hard.
Yes, it is, right? Because if you do plug in the 0, it is bigger than that right there. And so it satisfies that, so we do include it. Soft or hard here?
Soft.
Okay, union that with the next interval, which is where?
x2 to x3.
Okay, and x2 is 7 pi over 4. Up to all the way up to here, it's bigger, right?
Yeah.
And so x3 is 13 pi over 4. Do we have any more intervals?
Oh.
Ah, I didn't even notice that.
So
It is bigger there. Look at that. And so from where to where?
x4 to 4 pi.
So 15 pi over 4 up to 4 pi, and then do we include it or not?
We include it.
Yeah, because you plug in the 4 pi, what pops out? A 0. Is 0 bigger than that number? Yeah. Okay, so this is super important stuff. I really want you to get used to that. The answers in the back of the book will be given like this. It'll say where x is less than or equal to 0, less than 5 pi over 4, comma, da 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 da. I think this is easier, much easier. If you prefer to do it this way, okay, but this, I mean, I love the visual. You could just see from there to there. Is that right? Yeah, it's that right there. You're not including the endpoints, you know. I prefer to grade them that way also, but you know, whatever. So, okay, any questions about that? Nope. Okay. All right. That's the same thing. Yeah, we'll do it. Why not? Okay. Okay. So, this is the same type of problem. same as the first type. So all we're doing is we're just finding the exact values for where this thing is equal to, in this case, -1/2. What's the first thing I'm going to do?
Graph cosine.
Graph cosine. And cosine starts where?
At 0. Oh, no.
At 0. When x is 0, the output of cosine is
What?
+1. So it's the one that comes down, comes back up. Comes down, goes back up. So that's 2 full periods there. So that's 4 pi. This is 2 pi. This is pi. This is 3 pi. We have pi over 2. 3 pi over 2. Another reason why this is so useful to mark it out like this. Like I said, get in the habit of marking the maxima and the minima and these and that. Because when it's just sine and cosine, these happen to divide up the quadrants as well, right? You know you're in quadrant 1 if you're here. You know you're in quadrant 2 if you're here. 3, 4, and so on, right? So that's nice. Okay, basically same picture. Since this down here is -1, the -1/2 is right here. So I'm expecting 1, 2, 3, 4 answers. One's going to be here in quadrant number what?
1. No, 2.
2. So x1 is in quadrant 2. This is x2 and it's in quadrant what? 3. This is in quadrant what?
1. Right?
This would be quadrant 1.
Oh, yeah.
This would be quadrant 2. But again, like that's not how we're going to figure this out, right? We're going to find these. Since these are just repeats of these, we really only care about these. But okay. So, what triangle do you know has a 1 and a 2 in it?
30, 60,
30, 60, 90. So let's draw that guy, okay? Notice I don't care about orientation. This is how I always draw this triangle. What are my angle measures in here?
Pi over 6 and pi over 3.
And so cosine of which one of these gives you 1/2?
Pi over 6. Wait, no, pi over 3.
Pi over 3, because if you're here, adjacent over hypotenuse would be 1/2, right? So, in other words, cosine pi over 3 is 1/2. Now we just need to figure out, okay, so then pi over 3 is going to be our reference angle. So there's, I guess, 4 possibilities. It's either this one where it's actually pi over 3, it's this one where that one's pi over 3, it's this one where that's pi over 3, or it's this one where that's pi over 3. Everybody get my drift here? Why it's really nice to think about reference angles? Like, we know that the reference angle has to be pi over 3. The only difference is going to be the plus or minus. And so now we know where these guys live, right? X1 you told me was in quadrant what? 2. And so if that's pi over 3, then what's this measure? Measuring all the way over.
3 pi over 3. Oh, no, 4 pi over 3.
4 pi over 3 would be down here.
Oh, so 3. No, it's 2 pi over 3.
2 pi over 3. See why I want you to have this down where you could like wake up from a dead sleep and just write it out? It's going to help you, right? Like you don't have to think, but like I know that that's 2 pi over 3. I just know that's where he lives. So that gives us x1. I'm just going to go ahead and do it like this. x1 is 2 pi over 3. I'm going to stop and say, yep, 2 pi over 3 lives between pi over 2 and pi. So yeah, we're good. What about x2? What quadrant is he in?
3. That would be 3 pi over, no, 4 pi over 3.
Right, because this is 3 pi over 3, so this must be 4 pi over 3. And so this is equal to 4 pi over 3. And so we just add 2 pi to each one of these, right? 2 pi would be 6 pi over 3, 6, 7, 8 pi over 3 for this guy. And then this guy would be, I said 6, 7, 8, 9, 10. 10 pi over 3. Right there. Yeah. Questions? Concerns? Comments? Another thing to notice is like, we're asking where is cosine negative. Cosine is the x value on the unit circle. So you know that your stuff has to be over there. Right?
Yeah.
I mean, and there's, so you could do it that way. I guess you could do it that way. I think this is going to be your best friend though. Like really, there's no guesswork. And it's very simple to just mess this up and be like, oh yeah, tangent's positive in the second quadrant. And so it must be the second quadrant thing that I'm looking for.
We're going to do this with tangent.
That's the next thing we're doing. And so, but no, tangent isn't positive in the second quadrant. Tangent's positive in the third and the first. And so you just messed up because you just got a sign backwards. Whereas this, there's no question about what's going on. We're looking for that point, and that point, and that point, and that point, right? So, okay. Same deal, except changing this. Any questions about that? Any questions yet? Okay, good. So, now the interval has changed to negative pi over 2 up to 3 pi over 2, not inclusive. And we want exact values where, and this is what 48, this is number 48 from your book. We're looking for where is tangent of x equal to the square root of 3. What's the first thing I want to do?
Draw tangent.
Let's graph it, right? And I'm going to graph it on the interval it tells me to. So, okay, first things first. This is how I like to draw a tangent. I'm going to start here. I know it comes up and it comes down like that. Where is this first asymptote?
Pi.
Over 2.
Oh, yeah.
Yeah, get really good at that. And that, therefore, this guy is where? Minus pi over 2. I don't have everything yet. I need to go over one more. And so the next bit, if I drag him over, that'll put him at pi. Goes up, comes down, and then here is your 3 pi over 2. Okay, and so now we want to know where is the output equal to the square root of 3. So I'm just going to draw a square root of 3 right here. Here's square root 3. And I'm just going to ask, okay, where is that? And so how many solutions do I expect?
2.
2 solutions, because if we go back, they didn't ask us to go back. But they could have asked us to go back to like negative 500 pi over 2, and then we'd have an extra, I don't know, whatever. So I'm expecting 2 solutions. One of them is going to live here in which quadrant?
1.
Quadrant 1. The other one's going to live in quadrant 3. So I'm going to call this x1, x2. Now, what triangle do you know has a root 3 in it?
36, 90.
See how why we had a quiz on this stuff? Like, this is going to come up for the rest of the class. This is like the workflow that's going to be going through your head. Like, you're going to have something like this. Okay, I know I have a root 3. Well, if the output is root 3, what do I know that has a root 3 in it? Well, it's this triangle. And so now the question is it tangent pi over 6 or tangent pi over 3 that gives you the root 3?
It's
Over 1.
pi over 3.
Because tangent is opposite over adjacent. And so tangent of pi over 3 must be root 3 over 1. And so, right, and this is what we're doing here, right? We're saying, there's this triangle. Here's your pi over 3. We know that this guy has lengths of 1, root 3, and 2. And if you go opposite over adjacent, because that's what tangent is, then tan pi over 3, which is opposite over adjacent, is root 3 over 1, then that gives you the output you're looking for. So x1 must be pi over 3. beg you not to put your answers like I just did right here. Like, please have it like x1 equals this, x2 equals this, like, and have that boxed somewhere on your page, right? Okay, so now we know that the other one is in this quadrant.
So, third.
What must that be? What's the actual radian measure of the full thing?
Wait. Oh, it's
That's
7.
3 pi over.
Oh, 4
4
pi.
pi over.
Oh.
There we go. 4 pi over 3. Right? That's basically, so there's a bunch of ways of thinking about this, right? We have your triangle, and if you were to put it right there, and then you'd have your opposite over your adjacent, and the signs would be correct. You could also think about it as if you took this thing, placed it in the correct orientation, the correct place, and then shrunk everything. So that that's 1. This would be that, so I'd have to divide that by 2. That would be 1/2, or negative 1/2. This length right there would be root 3 over 2. Right? And so then the point on the unit circle would be the point minus 1/2 minus root 3 over 2, which would be your x and your y value. And we know the tangent is y over x. And so negative root 3 over 2 over negative 1 over that does indeed give you a positive root 3, right? We're all saying the same thing. I find it's much easier to not go to this step where you're starting to write in the lengths, because you should be at a point now where you know that if you take that and divide it by that, or if you take that one and divide it by that one, it's the same thing as if you had shrunk it and then found the coordinates, right? And so this is why I did suggest, like I said, we could have started by just defining it on the unit circle and then saying cosine is the x value, sine is the y value, and we could just plug along. But this is so useful here, because once you figure out, okay, tangent is this, well, now you only have 4 possibilities of where this guy ends up, right? And it'll always be, in this case, root 3. It's just, is it plus or minus, right? So, okay, there you go. We got that. Now, we already talked about the kind where it's going to say, give me the interval where something is bigger. So we could do that here if we wanted to. We could say, find the intervals on where, here where it's less. And we'd say, well, I guess it's from negative pi over 2, not including it, all the way up to pi over 3 would be where it's less. And then again from negative pi over 2 all the way up to 4 pi over 3. That would be where it's less. Where it's bigger would be these intervals here. And so from pi over 3 to pi over 2, not including. From 4 pi over 3 to 3 pi over 2, not including them, the endpoints. Right? So, we're not going to go through all that. So, okay. That's that.
Will they ever give you like root 5 or like a value that's not on the triangle?
Not for exact. We will do where we will have ones that you'll have to use a calculator for, but I'm going to use those sparingly, like very sparingly. Anytime they're asking for exact values, this is what they're asking you to do. And in every case, there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possibilities. And you should know where all of those are. You should be able to look at this and go, yep, that's 7 pi over 6. Yep, that's, oh man, come on. 5 pi over 3. Right? You should know where all of them are so well that this problem becomes trivial. That this homework is going to be so easy. Okay, here we go. This is the part where it says graph without plotting points. Okay, so 56, we want to graph y equals 3 plus cosine x. Now you know what cosine x looks like, right?
Yeah.
Yeah.
Right? Okay. And so what does adding 3 to something
shifts
do
it
to
up
it?
3.
Just shifts it up. Now, one thing I'll say about this, every one of these you're going to get, oh, actually, we'll do that in the next one. We'll do that in the next one. So, now here's the thing. Remember where this goes from. It goes from positive 1 down to negative 1. So if we shift it up by 1, all of those little troughs, all of the minima, would touch at one place. Now we've shifted it up way more than 1. We're way up at 3. Okay? So, one way you could
They
do
all
this.
go like that too.
They're going to go between what number and what number?
2 and 5. Yeah, 2 and 5.
2 and 5, yes. No.
Wait.
How about 2 and 4?
Oh, yeah.
And this is what I suggest you do. When you have an upward shift, draw a fake x-axis.
Yeah.
So it's like, okay, it's as though I did have this down here, but now it's been shifted up to 3 in this case. And if that's my x-axis, I know cosine, and now I'm forgetting all about this altogether. Now I'm just going to draw cosine. I know cosine starts up here, comes down, goes up. And I think it says to draw on the interval negative 2 pi up to 2 pi. I think it might not say that, but I'm pretty sure that's what it has you do. And so now, as you can see, and so now the only thing that's left, this goes from what to what?
4 to
4.
Yeah.
4, there's a 2. That's what I'd like for you to do with this one.
Okay.
And this is a good practice to get into, especially the stuff we're going to get into later, like being able to tell where these max and min points are. Now there's no other intersection, so we're not going to worry about this. If it were a different type of problem, I would want to figure out where each of these happen. So for instance, I would say that we do this, but this is not that type of problem. We're not going to worry about this just yet. Although this is really good practice. But whatever, I'm not going to require that you do that. But wherever it does go through, we do want to have something. So that's that. That's very simple. Questions before I erase this guy? All right. Now, here's another. 58. Y equals. So it says graph this. The problem is in your book, it writes it like this.
So it looks like it's stretched.
So it looks like, so it's ambiguous. Is it?
Yeah.
Is it like this? Is it like I wrote it there? So in this section, every one that you're going to do, they're not shifting the inputs.
Okay.
And yeah, so yeah. Basically, you could use this rule of thumb that what your book does is anytime there's not parentheses, then the very next thing you see here is by itself. Like in other words, if they did want to say x, the sign of x minus 1, then they would have put parentheses around it. But I think it's completely ambiguous, and I would just rather use parentheses every single time so there's not this thing. So this does not mean sine of x minus 1. This is sine of x minus 1. And so this shouldn't be too hard. And again, I'm going to do the same thing. I know what sine looks like. Now since we're subtracting 1, we're going to take the graph of sine and shift it down to minus 1. And so I'm going to start by doing a dotted line this way. And now I'm going to forget that the x-axis exists. And I'm going to say, okay,
It's going to touch.
starts here. Yeah, and it is going to touch right there. Right? Because if normally sine goes from 0 up to 1, so this is what part of this exercise you're going to have to use your brain and say, wait a second, hold up. Yeah, I can't just you can't just do this and be like, oh, it's negative 1, okay, all right, done. Like, no. Use your brain because this one definitely does intersect.
Will they ever shift it by less than 1, so you have to then find all of them?
That will be, yeah, I don't know, I'm not sure about in this homework, but we're certainly going to do that. Absolutely, we'll be doing that. And so this comes down, it comes back up. There you go. And this occurs at what point?
Pi 1. No, pi over 2, 1.
Just pi.
Pi over
Wait,
2. Pi over 2.
Oh, yeah.
Right, because that's 2 pi.
Yeah.
So half of it is pi. Pi over 2. And then comes down, comes back up, and hits at what point?
Negative pi over 2. Oh, wait, no, negative pi.
Wait, what?
So this would be negative pi over 2.
So negative
3 pi over 2.
Negative 3 pi over 2. Be careful. That's why we're doing this, right? So you get that. So all of this, you can iron out all of these kinks right now. And if you're doing this, it would probably be nicer. It would look nicer to label them up here. I don't care really, but it just, I guess that looks nicer. I'll know what you mean. Okay. Okay. That's that. Never mind. So for this section, it's all vertical shifts. We're either going to shift up or down. Even if it does this, and you're like, well, wait a minute. Do they mean to shift it? Or do they mean to uh-oh. Like, we're only doing up and down shifts right now for this section.
Because if you just shift it like pi
What
over 2,
if you
then it's
did
just
stretch
cosine.
it by 1?
So,
Depending on which direction.
yeah.
Right? But yeah. If you minus off pi over 2, then you
Wouldn't
end
it
up
be
with
either?
cosine.
Because
No, because think about it. So it does this. If you shift it that way by pi over 2, then you end up with
it would be like upside
being like, it would be, right. So in other words, sine x minus pi over 2 would shift it that way, and you would be the same thing as cosine. If you shifted it this way by pi over 2,
it would be upside down.
it would be upside down cosine. And what would upside down cosine be mathematically? How do you flip something upside down? So
Multiplied by minus 2, negative
1.
cosine.
Negative.
it would be negative. So if you add pi over 2, you end up with a negative cosine.
Wait.
That's weird.
That's right. Adding shifts it. Wait.
Wait, I thought if you add to the
You're right.
it allows-
I was wrong. So
Oh,
adding shifts left.
Yeah.
Good catch. Subtracting shifts right. And there you go. So subtract pushes it to the right, and you get negative cosine. Add shifts it to the left, you get positive cosine. Yeah, but we'll get there. We're not doing that this time, just yet. Okay, questions? These are pretty easy. Just be careful. Yeah, we saw where we had a couple points, right? Like, it does touch. It does touch the x-axis. And then we had also, okay, that's pi over 2. Oh, so that one must be negative pi over 2. No, not even close, right? So careful, there's a bunch of little pitfalls here. Okay, 79, 81, and 83. They give you stuff like this. 82 says, as x goes to 0 from the right, f of x goes to L for some real number. For some real number L.
So it's just any real number.
Well, no. Then it says, use a graph. Use Desmos to predict L. So in other words, they're going to give you a function. Here's one that they're going to give you. F of x is equal to x plus tan x over sine x.
Oh, so we have to
Now here's the thing. Yeah, now just wait a second, because I want to talk about this, right? So if you graph it, this becomes the easiest thing in the world. But if you say, well, let's just see what happens if I plug in a 0. Let's see what happens when we plug in a 0. What is f of 0? Well, 0 plus, what's tangent of 0?
Undefined, right?
Nope.
Oh, 0?
Think about the graph.
It's negative. Oh, well, yeah. So it's just 0.
So it's just 0. Okay, so 0 plus 0. What's sine of 0?
Negative 1.
No. 1. It's undefined. Wait, 0.
Is 0, right? Think of the graph. Again, sine starts here, comes up, blah, 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 blah.
So
From
you
now on,
can't have that.
sine means
Divided
this
by
graph.
0, but it's still 0. Wait.
So it's 0 over 0.
Go to them.
Wait.
Uh-oh.
Wait, but you're dividing by 0, but it's
Uh-oh.
1?
Uh-oh.
No, it's
I don't know. What is it? And that's the thing, right? Like, it might be 1, it might be 0, it might be undefined, it might be any real number.
Anything divided by itself is 1, but anything. zero
Yeah, but
divided by
it
anything
depends
is
how
0.
fast one of them is going to 0 versus the other. So, when you graph this on Desmos, you're going to see this. And a bunch of other stuff, and it's doing a bunch of crazy stuff. Yeah, you'll see. And this right here goes through at the number 2. So when you graph that, what do you predict is going to happen as we get closer and closer to 0? The graph. What's L, in other words?
2.
That's what this is getting at. So it turns out that this guy approaches 2 as x. It goes to 0 from the right. Yeah. Yeah, if you take calculus, I could show you real quick why that's true. But what I want to do real quick is let's change this up a little bit, and you can see how this might be the case. Okay, so as x goes to now instead of 0, let's say x goes to 1. It doesn't matter from which direction. But as x goes to 1, f of x goes to L for some number. And now let's say that f of x is this.
Oh.
Wait. Oh, that's just a parabola.
Well, if we plug in
Oh no, that's
line-
just a line. That's just.
Well, here's the thing. Now let's just look at the similarities here. Let's look at the similarities. If I plug in a 1, let's see what
you get the
happens.
same thing.
I get a 1 minus 1 is 0, times who cares is 0,
So it's just
over 0. Oh. Well, but now if you just plug this into a computer and said, hey computer, every time you compute f of x, I want you to do this. Plug x minus 1. Multiply that by that. Then divide by this right there. Then you give it 1, your computer's going to go, and undefined, because
so
it's
not just going to give you the line.
But you can
dividing by
x
0.
plus 2.
But look at this.
you can simplify.
Yeah, you could, but we're not computers. We could simplify this and say, wait a second,
Just x plus 2,
it's just x plus 2.
which is 1.
Wait, so the computer wouldn't just give you the line x plus 2 if you...
Some computers will. I'm saying, like, if you hard code, if you give a computer explicit instructions telling it to do this, then divide it by that, it will say division by 0, I can't do it. Now, Desmos is smart enough to know, hey, hold up, wait a second. Well, that's not what you're doing. Like, I could do this a bit easier than that, right? And it turns out, yeah, so this is what I'm saying. Like, look at what happens. Something actually cancels out. The way it's written, you cannot just plug in a 0. But it turns out that you cannot just plug in a 1. It's the same thing as 1 plus 2, which is the same thing as 3, if you cancel something out. The way it's written, you get division by 0, which is bad. But if you can cancel something out, if there's something there to cancel out, then there's no problem. That's what's going on in here. This thing right here, it turns out there is something to cancel out. You'll have to wait. You'll have to wait for calculus to figure out how that works. But it turns out that there's an x that can be factored out of everything. It turns out,
How?
yeah, it turns out that this is the same thing as x times something, and that this is the same thing as x times something else. And so it turns out that this can be written as 1
Same as
times
x
something,
times sine over x.
x times something else. Those guys cancel, and you end up with x plus something divided by some other thing, and then when you plug a 0 into it, you no longer have that pesky division by 0. Just like in this case. It's like something can be factored out. In fact, it would be better if I had written it like this, to say x squared plus x minus 2. At first glance, you might think, I cannot plug a 1 into there. You'll get division by 0.
Yeah.
If I tried, I would get a division by 0, and so that's not going to work. But then if you say, wait a second, hold on, maybe there's some magic I could do, which in this case there is some magic you could do to rewrite these things so that an x cancels out. Same thing here. You could rewrite this so that an x minus 1 cancels out, and you're left with this. And so that's what's going on here. And each one of these that you get, like if you just plug in the number, and I think in every case it's 0, and it says to approach it from the left or from the right. In every case, if you simply plug them in, you would get a division by 0. But there's some magic behind the scenes that you could do. Same way there's magic behind this scene that you could do to actually cancel some stuff out. That's what happened. That's what's going on with this. They don't bother to tell you this because it's supposed to be a mystery until you take calculus. But yeah, so that's what's going on. They're good ones to do. We're skipping the application problems for this section. So, a little bit of housekeeping. We're going to have to do a quiz soon. And what I'd like to do is, in fact, I want to, and here's the thing. This might sound mean, but I'd like to have 2 quizzes. Because the more quizzes you have, the better your chances are, right? And I'm thinking, what I'd like to do is for the first quiz that we do, it'd be another one of those like in the first 10 minutes of class.
Oh.
And all it would be is you draw sine,
Oh.
right? 2 full periods of sine on either side. You label like this, you label like this. And you call it sine x. And you let me know that that's an x, and so on.
And all the other ones.
Not all the other ones. Because really, like, if you know sine, you know cosecant.
Yeah.
Right? Cosecant's just the one that shoots up this way. It shoots down that way.
So just the 3.
So I'm thinking just the 3. And this is what your quiz would be. Okay? Because, like, right now, I'm just gonna stop after you. I'm not gonna put all the other ones in there. But this would be your quiz. And then I think with tangent, it's good to do 3 full periods. So 1 right here in the middle, and then 1 on either side.
Yeah.
Right? And we could identify that that's pi over 2. That's pi.
And we draw the asymptotes.
3 pi over 2. Absolutely, you draw the asymptotes. No asymptotes, no credit. I like that. That's going to be my new mantra. No asymptotes, no credit. Okay? That right there, I didn't bother to write the things in, but you know, you get the idea. I think that should be quiz 2. We just come in one morning, we do it, it's done, we're happy. And then we could have a more substantial quiz over all the stuff we've covered up until now, because this is the end of this section right here. And yeah, so I think that's what we're going to do. It's up to you guys whether you want to do this Thursday morning or Tuesday morning. Just don't get with me yet. Just email me.
This Thursday or?
Either this Thursday or this coming Tuesday.
Okay.
I'm not partial either way. There's one more. Oh yeah, and this is, so finally, okay. So we've talked about sine and cosine and thereby all the other ones in a bunch of different ways. And when you think, it may be at this point that in your head, when you think sine, you immediately think opposite over adjacent, or opposite over hypotenuse, right? That's cool. This is how you want to think of sine for the rest of your life, right here. Sine is this function that does this. Now the other things are good, and you can see why, right? Because like, if you have this equation, sine x equals root 3 over 2, it's really good to be able to say, root 3 and 2, that's the one, that's this guy, and so opposite over hypotenuse, x must be that, and all the others that it could possibly be, right? Yeah. But this is really good to remember that sine is indeed opposite over hypotenuse. That's cool. It's good to remember that it's the y coordinate on the unit circle. That's also very good. In fact, that's going to be fundamental later, that this guy, that sine is simply, sine keeps track of where the height of the point is given any angle x. That's a good way of thinking of it. But from now on, this is really what you want to have in your head. If you want to pin sine to anything, pin it to this function right here. It's the function that looks like this. It goes, it does this. And yes, that's like how we got that, was from the unit circle. It has this property too, which is something you don't want to forget. But really, this is what sine is. This is what cosine is. This is what tangent is, and thereby all the other ones, they come from this. It's better to think of them as graphs. So anytime somebody says, yeah, so I have this equation, it's sine x equals x. What should go through your head is, well, this is what sine x is. Or I should say, I have this equation in my head, cosine x equals x. What do I do with that? The first thing that goes through your head is, well, this is cosine. And if that equals another function, x, then it looks like this. It's the intersection right there. And maybe, I don't think it does. I don't think it actually goes through there. But nonetheless, I could tell you, well, I think that this equation has one solution. Why? Because you thought of cosine in terms of a function, right? And like a million other things, especially in calculus, thinking of it like this. This is nice, this is where it comes from, the opposite and adjacent, that's helpful, don't forget it, but this is what they are from now on. They're these functions that look like this. That's what their graphs look like. Cool? Yeah. All right, guys, I think we're done. Unless there's any questions. Any questions at all?
When will we start pre-calculus?
This is pre-calculus. This is it.
Okay,
This is
so
it.
it's just like,
Yeah,
okay.
this is what pre-calculus is. This is the last. The trig functions are the last thing you need to know before you're ready for calculus.
Okay.
Everything else is we covered in algebra 2, especially the way that I did it. Like, might be a couple things here and there, but like, really, this is the last bit of chops, the last stuff in your toolkit that you need in order to go to calculus. And we're going to go pretty deep into this stuff too. We're going to talk about, later on we'll talk about vectors and parametric equations. Polar coordinates, stuff like that. So real quick, polar coordinates. We actually talked about this before. We talked about this last year. I said, you know, if Joe lives here and Sam lives here, now if they're on a city block, if they're on city blocks, it might make perfect sense to say, all right, Sam, go 5 blocks east and 2 blocks north, and you'll get to my house. But if we live out in the country and there's just fields between us, it might make more sense to say, you know what, Sam, if you go this many degrees and walk this far, and you end up with the same thing, right? You could give a radius and an angle, and I could tell you where any place on the plane is. I could also do that with explicit coordinates like this. when you do this, this is called polar coordinates. So, for instance, I want to convert the point root 3 comma 1 to polar coordinates. What I'm going to do is say, well, I need a radius and I need an angle.
The radius is 2.
The radius is 2, because if you notice the way I set this bad boy up, that length right there is 3, that length right there is 1. You know that's 2. And then what's that angle? Pi over 6. And so we could say this point it's exactly the same thing as saying 2 comma pi over 6. I could give you 2 pi over 6 and you'd know that you'd end up there. Or I could give you this and you could tell me that. They're actually equivalent, right? And we talked about this in terms of complex numbers, right? Like if you took a complex number here and another complex number, say here at 1 comma root 3, and if that's at 1 comma root 3, what's its radius?
2. Okay.
And again, it's the 1 root 3 2 triangle. And so what angle is that right there?
Pi over 3. Yeah.
Pi over 3. So we could say, that's the same thing as in polar coordinates 2 comma pi over 3. And I said complex numbers have this interesting property that when you take two complex numbers, so for instance, let's take the complex number that lives here, which would be root 3 plus 1i, and I multiply it by this one, which lives there, which would be at 1 plus root 3i. When we multiply them together, we go first, outer, inner, last, we get root 3. Outer is root 3i, so plus 3i. Inner is 1i. Outer is negative root 3, right? Because I squared is negative. Root 3 and... oh, that's just root 3. Yeah, so the root 3's cancel. We get 3i plus i, so a total of 4i. But we also said last year that with complex numbers, the radiuses are what and the arguments are what when you multiply those two numbers together. The radiuses get multiplied, right?
Yeah, I know that.
And the arguments
Are added.
are added. And so let's see what happens when we add. When we multiply these guys, we get a new one, which is 4. Add the arguments, and you get what's root 3? Pi over 3 plus pi over 6.
3 pi over 6. Wait,
Which is
no.
what?
Yeah.
Pi over 3.
How about pi over 2?
Yeah.
And where is 4 pi over 2?
Just 4.
It's 4, and it's straight up, right? Because pi over 2 is right here. And if the radius is 4, it's right there. And is that at 4i?
Yeah.
You better believe it is, right? So these things are, yeah, I love this stuff, man. And so that's, yeah, there's a really cool reason why that's true that you won't know for quite a long time. But, like, yeah, so anyway, polar coordinates turn out to be very useful, especially in calculus, like some problems that turn out that are ridiculously hard to solve in Cartesian coordinates become very easy in polar coordinates. Kind of like this problem. This isn't really the kind of thing we're talking about, but notice what we had to do, given those two numbers, to multiply them together. It's kind of a pain. But if we converted them into polar coordinates, it's like, well, 2 times 2 is 4. That plus that is, oh, that's 4. Oh, you're at 4i. Right? And so that kind of gives you an idea of how a hard problem can be turned into a very easy problem by thinking of the coordinates in different ways. And so that's something that pops up in calculus a lot, is converting the polar coordinates. So we're going to spend time talking about it. So that's why this is pre-calculus, right? Like a lot of this stuff. Trigonometric substitution, which is another thing. It sounds ridiculously hard, right? But it's basically, and like we're not going to talk about this much, but being able to do it is going to be invaluable for you. So in calculus, you're going to do something called integration. And just don't worry about it. And so if you have a function, say like this could be ridiculously hard to solve, and you could literally, using the tools that you learned up until the point, like you could literally work on this all night and just work in circles and circles and circles and do this for days. But when you stop and go, wait a second,
That sounds like something.
this looks like a triangle.
For days.
Like,
Realizing
for
how
instance, if I have an x here and a 1 there, then this turns out to be the square root of 1 minus x squared.
Oh.
And so then that over that would be what in terms of theta? Well, that over
Cosecant?
that would be, well,
No, just secant.
cosine. So secant, so it turns out that secant theta is 1 over that right there. And so you do some magic and figure out that this is the same thing as secant theta. Your dx turns into something else and blah, 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 blah. But that's the idea. And again, you take a problem that's literally impossible to solve and turn it into something that turns out to be so simple that you go, oh, it's equal to 1. And you know, it's like, yeah, oh, that's obvious. So these are the kinds of skills that we're building right now that are like fundamental in calculus, and this stuff shows up all the time. Like these pictures you will draw every other day when you're taking calculus. And so this is pre-calculus. That's what we're doing. Yeah. Any other questions? Any other questions at all? Well, that's good. Okay, we're done, guys.